the pairing of W2M with itself, that's what I call A to M, is a rational function of nu. And you can compute those recursively. There's the recursion relation. And so I said A0 of nu is chosen to be 1. And then if you look at this first recursion relation with m equals 0, that tells you that A plus or minus 2 has to be 1 minus nu over 1 plus nu. And A plus or minus 4, you get 2 factors. And it goes on like that in a very simple way. That's the invariant Hermitian form on SL2. It's a really simple thing to read off the signature from these formulas. Well, in fact, that's basically the way that this was classically done for SL2. More or less, Bardman wrote down formulas like this, and he said, oh, okay, if you look at these formulas, the only way all these constants can be positive is if nu is smaller than 1. That's basically the story. But just to look at these formulas and read off the answer, that method doesn't generalize to other groups so well. So I just want to know that there is this rational family of forms, and well, I wrote down exactly what it looks like to be concrete, but it's not these exact formulas that we're going to use. Okay, what are we going to do? So I want to make sense of the signature, and well, as I said, the form is going to be sorry. Well, I said positive or negative. In fact, positive or negative or 0 on each m. If I look at this form again, the form is 0 on all these A plus, on W plus or minus 2, plus or minus 4, and so on, when nu is equal to 1. So if nu is 1, all these constants are 0, and only the W0 survives. Anyway, always you get this string of plus or minus signs. So for example, here's what the string looks like for nu between 3 and 5. So you could read this off from the formulas in the proposition on the previous page. So in particular, well, Atlas will compute this formula for you, and when you look at it, you see these representations are not unitary because the invariant Hermitian form is indefinite. It has both plus and minus signs. Okay, so what the strategy that we're actually going to use is to keep track of how the signatures change with nu. So we're starting out at nu equals 0. And well, I meant to write L2 of G. This is a tempered representation. It's weakly contained in L2 of G. At any rate, the signature is positive. And so, well, there's the signature. It's all pluses. Then, as I vary between 0 and 1, these representations remain irreducible. The form is changing in a rational way. So on each of these representations of K, you have a rational function which started out being positive at 0, and it's never 0 between 0 and 1, so it has to stay positive. That's the next conclusion. Then what happens at nu equals 1? Well, at nu equals 1, the Langland's quotient is the trivial representation. So the form remains positive. Well, it's always defined to be 1 on the trivial k-type, but the form becomes singular on everything else. So this form has a radical, and that's these k-types other than 0, these guys over here and these guys over here, and really the form is 0 there, that's why I put them in red, but well, this is some rational function which has a 0, but the derivative is I said it was positive, but I've been talking about a function which is positive before 1 and then has a 0 at 1. So to tell you that it has a positive derivative is not very plausible. It actually has a negative derivative. You look displeased, Mark. No? Good? Okay. At least you should have been displeased about this positive statement. It's a negative derivative. Yeah. In fact, we tend to think of the derivatives from the other direction. That's, oh well. At any rate, well, the conclusion is that all these rational functions have simple zeros at nu equals 1. And since they're simple zeros, after we cross them, the form becomes negative. So from 1 to 3, the signature changes at these other places. And it looks like that. So, excuse me, at nu equals 3, what happens is that the Langland's quotient is this three-dimensional representation of SL2. It's the adjoint representation of SL2. The form, well, on the three k-types of the adjoint representation, the signature is just inherited from this previous interval, but the rest of the form has a radical, that's these zeros, and again, well, they're simple zeros, and the derivative well, the derivative from above is negative. So after, yes, so again, I got the derivative from above is negative. And so the form changes sign. So all these minuses at 4, 6, 8, and so on become pluses, and that's what the signature is in the next range. So that's the idea of what's going on with this computation. So that's the end of the slides that I prepared properly. The conclusion is that this quotient is unitary for nu in the closed interval from 0 to 1. By the way, we've mentioned this several times. In these atlas parameters, the set of unitary points has to be closed. Being unitary is a condition of definiteness for a form, semi-definiteness. And being semi-definite is a closed condition. Something is greater than or equal to 0. And so in any reasonable parameters, the unitary representations have to be closed. So we do get this closed interval, And of course, I've written it incorrectly here. This should be an open parenthesis. Starting at nu equals 1, well, above nu equals 1, we get non-unitary. Because what happens is that for all nu greater than 1, the signature, well, it's always plus on the trivial k-type. And for nu bigger than 1, it's minus on the 2 k-type. There are other interesting things going on for bigger values of nu, but for those two representations of k, we're all done now. It's all plus and minus from here on out, and so the representations are non-unitary. Yes?
Does that do this? Let's say nu equal 1, do the same calculations for the power that corresponding to the legal representation of the discrete series, or it knows for the discrete series that they are unitary?
So the nature of the algorithm, I said always what we were doing was taking the continuous parameter and deforming it to 0. For a discrete series, there is no, the continuous part of the parameter is 0, and so we're always using this unitarity at 0, and so for a discrete series, yes, Atlas will just look at the discrete series parameter and say, okay, I'm done, it's unitary. That's exactly right.
So, hang on, I'm going to invoke my chairman privileges. I have to step outside, but one of the questions is what people want to see in some of the afternoon sessions, and seeing this example in Atlas is an option. So if you're think about that, if you're interested in doing that.
I think it's clear that the answer is yes. Yes?
At nu is equal to 1, the open subquotients of the discourse is also unitary.
Yes.
Is that something general that when you reach the...
Yes. We have this rational family of forms. So at nu equals 1, this rational family on this discrete series has become 0. But if you renormalize by dividing by nu minus 1, it's clear that you inherit a positive form there. And so yes, that's quite general, that if you have a unitary open region, then the boundary, all the composition factors at the boundary have to be unitary.
So I'm not quite sure I understand. You're looking at a form on J.
These forms, let me go back to, where was it? It was far back. We're always looking at a family of forms on the standard representation, and the forms descend. So what's nice about that is the standard representation, the space does not depend on nu.
That was my question. The space changes now.
Then what does it mean? Yeah, but
Unitarity is talking about the quotient, not about the standard.
yes, that's right. But we have this family of forms on this fixed space, and we compute the signatures. Well, the signatures will have some zeros in them, but we compute the signatures of that family of forms on that fixed space. And so at t equals 1, the form will be degenerate, but nevertheless definite. On the quotient, it will be positive definite.
Yeah, but isn't that just when the k-type 0 disappear? Why are you interested in what happens?
So at t equals 1, we're not interested in the k-types where the form is singular, but in this, where was?
So it's made for linguistic purposes for comparing
So, you're right that here at 1, I don't really care what was going on with these other K-types. But I would also like to know that in this range, the form has become indefinite. And so for that purpose, I need to know that at this radical, that those were simple zeros. That's, and yeah, so
You track the number of flips you get. You don't always get exactly always get a split flip, but you might have multiple flips at the same.
that's right.
That's what you're indicating with your plus or minus the red.
That's right. I mean, the red. Well, yes. I should have a different color for higher order zeros, of which there aren't any here. But the red means it's a first order zero, and therefore the sign changes. So let me see if I can find the slides about the Janssen filtration. Sorry. Okay. So here's a topic in linear algebra. I have a finite dimensional complex vector space and a family, one real parameter family of Hermitian forms that's depending analytically on this real parameter. And I want to say that generically it's non-degenerate. Okay. Then I want to define at t, the form will have a radical. So I want to introduce the radical of the form, and I'm always interested in the signature on the quotient by the radical, and I'm interested in how that signature on the quotient varies with t. That's the problem. And the simplest fact is that on the open set of t's, where this radical is 0, the signature is locally constant. So how do I refine that? So I can get a form on the radical. On the radical, this form vanishes at s equals t, but I can take the derivative, and who knows whether I got the signs in the right order. I think I'm taking the derivative from above, but who knows. I get a new form on the radical by taking derivatives, and then inside the radical, I get a smaller space where this limit is equal to 0. And so now, well, I've got a form, first of all, in the quotient, but then at the next level, I've got a form, and that has a signature. And at any rate, I've said this somewhat imprecisely, but Janssen explains how to make it precise. You get a chain of subspaces which is eventually 0, and roughly speaking, this chain of subspaces is defined by the order of vanishing of this Hermitian form at T. And what happens is that on each subquotient of this chain, you get a natural non-degenerate form, this Pi of T, Qi of T. And the statement is that the signature changes on the odd levels of the form. So when you go from T minus epsilon to T plus epsilon, you get changes coming from the odd levels of the Janssen filtration. So if you know the form for smaller values of T, this gives you a formula at higher values of T in terms of these levels of the Janssen filtration. So this is a precise statement of how this generic signature changes at a place where the form acquires a radical.
The odd is just kind of generalizing the fact that an analytic real function
It's
0 as odd order.
It's exactly that fact. So Janssen tells you that you can near enough diagonalize things as a function of T, and then it becomes exactly what you said, that an analytic function of T changes sign at zeros of odd order. That's all it is. There's some nice, mildly serious linear algebra required to diagonalize things enough to make that the problem, but that's exactly what it is. Okay, so crudely, that's what a Janssen filtration is. And let me, as I say, the slides are not well organized, but I will organize the slides so, yes.
The sum there is over all three, or is this?
Yes, this is the sum over all K, here. All the odd levels contribute something.
For a particular
These, this is the sum over from K is 0 to infinity. Well, it really only goes up to some finite place. I should say that so at this sort of bad T, you get these signatures PK of T, QK of T, and the sum from K equals 0 to infinity of PK of T, QK of T is equal to P of, and here's where I don't remember I don't remember how the normalizations are done. These forms reflect what's happened at slightly smaller values, and these things sum to the dimension of V, and well, at well, the sum over K even pk of t plus the sum over K odd qk of t, it is I don't know.
Okay, we use the black marker.
Okay. Anyway, these two formulas are related to this one. Anyway, let me do this a little more formally. So, so basically, if I have a general Hermitian parameter, gamma, and I get these gamma t's and these forms so remember, well, this is always the sum over irreducible representations of well, so this is the multiplicity of tau. And so this is Hom over K of E tau into this. And this space is this is independent of T. It's not independent of tau. And the dimension is the multiplicity. Well, so I'll write this. The dimension of this space, I tau quotient gamma. Sorry, this was a T. Gamma T. It is the multiplicity of tau in the standard representation, and so that's independent of T. And so I call this maybe m tau of gamma T. It's a non-negative integer. Okay, and I said that now, if I had this Hermitian form, this invariant Hermitian form on here, and I fix these positive definite forms on these E tau, I put those two things together, excuse me, and I get Hermitian form on this space, on this multiplicity space, and this has signature, I'll write p tau of gamma t, q tau of gamma t, z tau of gamma t. And this is the dimension of the radical. And so these things are non-negative integers, this p tau plus q tau plus z tau is m tau. And these things, that's what we want to compute. So what does that mean? So what the theorem is that these multiplicity functions for I have some parameter nu equals 0 are, well, these things map k hat to n, and these things are linearly independent,